Welcome to another adventure of Mr. Warner Does Your Homework Quiz Edition. Alright, so we're going to go over some review questions for double integrals for calculus and hopefully get ready for our quiz that is coming up really quickly. So let's see here. We want to find the double integral of sine x over x dA. Alright, so remember what this is really looking for is a volume right here. The dA is the area of my base. S is the domain of my base. And they tell me that the base is created by the following triangle. Y goes from 0 to x goes from 0 to pi. So if I were to draw this out here, my y values go from 0 to some x value, and my x's go from 0 to, let's say, pi. So it's going to make this little triangle, y equals x. Now, what they're really telling me here is that my y's go from 0, of course, to x. So they're telling me I'm using a vertical rectangle. So my y's start at the bottom and go all the way to x. So I could rewrite my volume as follows. Sine of x over x. Because I'm doing my triangle, I'm starting with the vertical. This goes from 0 to x. And my x's will go from left to right, from 0 to pi. So we are going to go dy dx. So my changes in y's go from 0 to x. My changes in x goes from 0 to, let's say, pi right there. So when we take a look here, when we start integrating this right now, let's see what we got here. I am going to first integrate with respect to y. And that's going to give me sine of x over x times y, evaluated from 0 to x. Oh, this is nice. The x's are going to cancel, and we're just left with the sine of x, which we're now going to integrate from 0 to pi of just sine of x dx. And the antiderivative of sine of x, of course, is negative cosine of x from 0 to pi. And we can just solve this out. The fundamental theorem using FTC. FB, f of pi minus f of o, 0. Let's see what we get. If we plug in pi, the cosine of pi is negative 1. So this becomes 1 minus, and of course the sine of 0 is 1. Cosine of 0 is 1, but it's a negative, so we get plus 1. Oh, that's nice. We just get the value of 2. All right. So let's take a look at number 2 right here. Let's see if we can set this up here. Ready? We want to find the volume of the tetrahedron formed with the bounds of this plane in the first octant. So I'm going to draw this out. Okay. So if I were to graph this, my x-intercept would be at, what is that, 2.5? My y-intercept would be at 5. And my z-intercept would also be at 5. So we have this tetrahedron right down here. And what we're looking to find out is the volume of this inside here. So we can do this pretty easily. But we need our base. So when we look at the base, remember we're going to look at the base on the xy plane. Although we're going to find out later on, we can actually put the base on any of the planes. We could even use the yz plane if we like to. We're going to talk about that when we get to more like triple integrals. So, if I'm looking at the xy plane, if I were to graph it, my x-axis intercept, if I look at this little line right here, my y-intercept's at 5, and here we are at 5 over 2. And we have this line right here. I can write the equation of this line, y equals 5 minus, this becomes rise over run, so y minus 5 over 5 halves x. And of course, if we multiply this, what does we? And if of course, if we simplify that, we can find out what, which of course becomes 5 minus 2x. So if I look at my base here, x's and y's, I'm going to start with my vertical rectangle here. So I can get my limits. My change in y's are going to go from the bottom, which is 0, to 5 minus 2x, bottom to top. And my x's are going to go from, let's see here, starting at 0, going over to 5 halves. So if I want to find the volume, And so here's where I'm at right now. There's my little rectangle. That's the same little rectangle. Now we're going to increase that until we hit the surface. So to get the equation of the surface, we can solve for z. Z, of course, would equal 5 minus 2x minus y. So to get my volume, my double integral, the area of my base, dy dx, where my y's are going from 0 to 5 minus 2x. My x's go from 0 to 5 over 2. And then my height, which is the surface itself, 5 minus 2x minus y. And that will give us the volume of our tetrahedron right there. All right, so let's take a look at a couple more. I'm going to skip number 3, let you guys work on that one. But let's go on to number 4 right here. It says, find the volume of the solid bounded by the following surfaces and the 3 coordinate planes. Okay, so this is my height. There's my height function right there. So that's my function, f of xy equals, and we can solve for z here, 16 minus x squared minus y squared. X equals 2, y equals 2. So this is kind of like giving my bounds on the xy plane. So, and the 3 coordinate planes. So if I look here, alrighty, so if we look at the base, we are bounded by x equals 2, y equals 2, and since we're bounded by the other 3 coordinate planes, we know we're only in the first octant. For example, here's x is 2, y is 2. So this is the only region we are looking at because we're bounded by, of course, the xz plane, the yz plane, and the xz plane. So we're looking at only the surface in the first quadrant. So that's going to really help me set up my base right here, especially my limits, which will give me my change in y, which is going to be 0 to 2, and my change in x's, which is also going to be from 0 to 2. So I can get my volume, the area of my base, dy dx, from 0 to 2, 0 to 2, and of course my height, 16 minus x squared minus y squared. So let's go ahead and solve this one by hand real quick. When we integrate with respect to y, we're going to get 16y minus x squared y minus y cubed over 3 from 0 to 2. And of course that's just going to give us 32 minus 2x squared minus 8 thirds. Okay. Alright, so let's see here. And if we integrate this one with respect to x, I don't simplify anything, we will get 32x minus 2 thirds x cubed minus 8 thirds x from 0 to 2. And of course that's just 64 minus, plug in here, 4 8 thirds minus, this becomes 16 thirds, and whatever that is going to be for us. Alright, and let's see, we got time, we'll do one more, number 5 right there real quick. These are kind of fun here. Find the volume of the solid under our paraboloid, x squared plus y squared, about the region in the xy plane bounded by y equals x squared and y equals 2x. So they're giving me my base right here. So looking at the base, ready, here we go. We're only in the intersection of these two, so the parabola y equals x squared and y equals 2x. So we're looking at this region right here. Remember, this is the region we're going to project to the surface of xy right here, which is right there. There's our f of xy right there. So we're projecting to the surface, and we're going to try to find that volume. So to do this, we have to come up with our base limits for the area of the base. We look at our limits. And again, I'm going to use a vertical rectangle. So my change in x's are going to go from my bottom, which is the parabola, x squared, to the top, which is the line, 2x. My y values, be very careful, where do they meet? 0. And where do they meet here? Well, I can solve that. Ready? So if we just set x squared equal to 2x, we know x is going to be 0 and x is 2. So my y values, excuse me, my y values go from x squared to 2x, where my x values are going to go from 0 to 2. So I can get the volume now. Volume equals our double integral, area of the base, dy dx. My y's are going to go from x squared from the bottom to the top, 2x. My x's are going to go from 0 to 2. And the height, I can just plug that in, x squared plus y squared. And you can solve that. Hope you enjoyed the video, and I will see you all later. Bye-bye.